Back by popular demand. Thought I'd help out with 8.4, the multiplicity of zeros homework ideas. So let's kind of go over some problems that are like the ones in homework and kind of hit some of the ideas. But I'll probably kind of bounce around a little bit, so you'll just need to watch what I'm referring to. I'm not going to go like in exact order like the homework will, but start off with one kind of like the first set of problems there where it says describe the zeros. On homework it says you use the stuff from the word bank to complete the phrases, but I'm just going to look at this graph and kind of just in general. So let's see here. So if I wanted to describe the zeros here, so first thing I see is passing through -3 there. So x equals -3 would be one of the zeros, and I would kind of describe that as, since it's passing, the graph is passing straight through that point, is that has a multiplicity of 1. Has a multiplicity of 1. So when the graph goes straight through like that, that's a multiplicity of 1. The next one I see is here is at -2. And notice how the graph is bouncing at that point. And so what that tells me is that there's an even number of roots. Or it has an even multiplicity, probably has a multiplicity of 2. We could see 2, 4, 6, 8. We really aren't going to do that to you because it's very hard to tell the difference between a multiplicity of 2 and a multiplicity of 4 just by looking at the graph. So usually when it's a bounce, we're going to say it's has a multiplicity of 2. So you could also say that. I'm just going to abbreviate that to mult. Next one I see, so this is a y-intercept. So here like y equals 12. Well, that's not a 0. So only x-intercepts are zeros, so that is not a 0. Next one I see is the 1. So x equals 1. And what I notice here is that so like the -3, the graph is passing through here, and unlike the -2 where the graph is bouncing, so it's passing through that point, but it's passing through with a twist. And so that's an odd multiplicity, but that's bigger than 1. So straight through is 1, and then through but with a twist in it is going to be an odd number bigger than 1. So like 3 or 5 or 7. And usually it's very hard to tell the difference between a 3 and a 5 and a 7 just from the graph. And so we would usually just use a 3 there. So, or you can just say it has an odd multiplicity. It's kind of the basic version of it. So just knowing that it's odd is kind of the basic part. Knowing that it's odd and bigger than 1 is the more like advanced part of that. So saying it has a multiplicity of 3. And the last one is this 2 here. So x equals 2. And so then notice this one is going straight through. It's not twisting, like flattening near the x-axis like this one. So I know it's kind of turning down here, but not looking at down here what's happening here. We're looking at what's happening right at the 2. It's going straight through there. Whereas here it's flattening right near the 1. Here it's bouncing right at the -2. Here it's going straight through. So it's more like this, where it's right at this point, it's going straight through. So I'll write this straight through. So I'm going to say that has a multiplicity of 1. So that's describing the zeros. Something else I could ask you to do with this would be, I know there's a problem necessarily just like this. It's kind of like the stuff on the back of the worksheet where you're asked to write the polynomial in factor form, but I can do that from, do that from the graph also. So I'll show you what that would look like. Let me fix this real quick. So write the polynomial factor form. So I want to start off with, y equals, or f of x equals. And then we have this a value that we don't know yet. So this will come up like when you do a problem like 16 on your homework. So we have this a value, and then from the zero, so each one of these is going to become a factor. And so the -3 is going to become x plus 3. And we always switch the sign, and then that just had a multiplicity of 1. So it's just going to be x plus 3 to the first power, or just x plus 3. And then the next one, the -2, would be x plus 2. But that's going to be squared, since we think that was had a multiplicity of 2. And then we went to the 1, so that's going to be x minus 1. And we think the multiplicity there was 3, so I'm going to put the 3 on that. And then the last one was the 2, so it gets x minus 2, and then that one had a multiplicity of 1, so I'm just going to leave out 1 power there. And then, so remember what a is, it's kind of the correction. Like, when we multiply all of these numbers here, we should get the y-intercept. So we have this -12 equals a times 3 times 2, but there's two 2's, right? It's 2 squared, so 2 times 2. And then we have times -1, but there's going to be 3 negative 1's. So times -1, times -1, times -1. And then we're going to have negative 2's, which is one of those. Right? So times -2. So if I multiply all this stuff here on the right side, so -3 times 4, so that's -12. And then 3 more negatives would be, so I have a -12 times 3 negatives, it's going to be a positive 12. And then times -2 would be -24. So all on that right side, I got -24a. And on the left side, we still have equals -12. So we divide by -24 to get a by itself. And -12 divided by -24 is a half. So a equals a half. So in factored form, I'd have y equals 1/2 x plus 3 times x plus 2 squared times x minus 1 cubed times x minus 2. And if you were to type all that into Desmos, you would actually see the graph that we were looking at there. So that's how you find a. If you remember that, we talked about that in, I think, section 8.2. So, alrighty, let's look at a different problem. So write a polynomial factor form from the given information. Again, this is like number 16. So we have certain zeros that were given here. So we have 3 of them, but we have some extra information about 2 of them, and then we have a y-intercept. So the first thing I want to do is kind of start the same way that I started the last one. I just want to, y equals, and then this a value that we don't know, and then I want to look at each of these zeros and turn them into factors. So we have x minus 2, but because it's a double root, it's going to be x minus 2 squared. And the next one is -4, so it's going to be x plus 4. So I'm always making sure I switch my sign. And that one doesn't say anything about anything special, so it's just assume it's a single root. And then I have x equals 1, and so that's x minus 1, but it says that's a triple root, so it's going to be cubed. So kind of the same way as we just did the y-intercept here, so 32 is going to be equal to all of these things multiplied. So this times this times this times this, but I just got to pay attention to any like double, triple root, stuff like that. So 32 is going to equal to a times -2 times -2, since that was a double root, and then times 4, and then times 3 negative 1s, kind of like last time. And I just want to simplify everything here on this right side. So -2 and -2 is going to be +4. +4 times +4 is 16. 16 times 3 negative 1s would be -16 again. So I got 32 equals, so I got negative 16 times a. And of course we're just going to divide by negative 16. And so then a would equal negative 2. So y equals negative 2 times x minus 2 squared times x plus 4 times x minus 1 cubed. Yep. Not too bad. Last example I'm going to do here. Write a polynomial with these zeros in factored form. We're going to assume a is 1 and then write that polynomial in general form. This will be kind of like problem 17 and then 18. This one will be more like 17 though because it has the imaginary zeros in it, whereas 18 has just all real zeros. But we're going to assume a is 1. So this one's a little bit simpler as far as that. Like we're just going to start off with the same way that y equals, but a is 1, right? So I just put a 1 there, but we're not going to need that. So then x equals 5. That's going to be x minus 5. And then x equals 3i, so it'll be x minus 3i. And then x equals negative 3i, so it'll be x plus 3i. So just watch your signs there. So there's our factored form. And I do not need that 1 there, so really this is the best way to write that would be like that. And so to go from factored form to general form, we want to distribute. And so remember, you can only multiply 2 things at a time. So I'm going to pick any 2 of these to multiply together. So I can multiply this one times this one, I multiply this one times this one, I can multiply these 2 together. It doesn't matter. What I really suggest is that when you have factors that are like different, like or like each other, like these both have imaginary numbers in them, that multiplying these together first is going to make your life a lot easier than if you multiplied these and then multiplied this one in later. Like you should get the same answer in the end, but doing these 2 first really should make your life a lot easier. So that's where I'm going to start. I'm going to take these 2 here and multiply them. It's just distribution. So, x minus 3i times x plus 3i. Oops. Of course, x times x equals x squared, and then x times 3i is positive 3ix. Or I is a number, it's not a variable, so it's more appropriate to put in front of the x. Then I have negative 3i times x, which of course is just negative 3ix. And we have negative 3i times positive 3i, so positive times negative is negative, 3 times 3 is 9, and I times I is I squared. So we just need to simplify this. Of course, x squared is just x squared, can't make that any simpler. What's really nice here is that these 2 terms cancel. So I had a little bit more I terms. And then reaching back into our memories, remember I squared is equal to, or I squared is equal to negative 1. So this really says negative 9 times negative 1, which of course is just 9. So this really just says plus 9, positive 9. So we get x squared plus 9. So that's going to go back into parentheses because we're not done. X squared plus 9. And then I'm going to bring that x minus 5 down from above that I hadn't dealt with yet. So that was multiplying these 2. So why, think about why I suggested multiplying those 2 together first, because we had these things with imaginary numbers in them. Well, look where we are now. No more imaginary numbers. And so this is the way it always should be when you take 2, what these are called conjugate pairs, that they're exactly the same except for one's plus and one's minus. They should always turn out to be, when you multiply them together, nice numbers. So imaginary numbers go away. So do those first. And then we'll just distribute this here, easy peasy. X times x squared, of course, is x cubed. X squared times negative 5x squared. 9 times x. And then 9 times negative 5. And there's no like terms there, so we are done. So y equals x cubed minus 5x squared plus 9x minus 45. Boom. Remember, we assumed a was 1. There's a 1 right there in front of the x cubed. So if that had been something different, we would have needed to distribute that last if we'd had a number there. But that's it. A little hopefully helpful video for 8.4. See you later.